Okay, going to continue our little discussion here of um, kinetic energy. We're actually going to change this into that mode so it can be a little bit easier. I'm just going to step through to where we were. Okay, kinetic energy is what we're going to talk about. So kinetic energy is the energy of motion, or the energy of a moving object. It's got a simple formula. It's a little bit hard to read, this one. It says a half mv squared. So the way we'd write this, I'll try to write it a little bit better. Just change to give me a pen to write with. We'd have this would equal 1/2 m and velocity and a little 2 there. That's how we write it, half mv squared. Where m is the mass in kilograms and v is the speed in meters per second. And we know from before, we've had this formula here, velocity equals distance divided by time. Okay, just a question here. Where do you think this equation is used regularly in most of our daily lives? So cars traveling at different speeds, cars versus trucks. What we're going to see here is doubling the mass of a moving object doubles its kinetic energy. However, doubling its speed increases its kinetic energy by a factor of 4. And that's because of this little 2 up here, this squared. Small increases in speed rapidly increases the risk of death or injury. And we'll see that down here in a minute. We'll just go to the next slide. Sorry, when we find... There we go, sorry. So here we just got this from the Road Traffic Authority of New South Wales. We could see that if you're travelling at these speeds down the left-hand side, and on the right-hand side here, it tells the risk of death or injury compared with travelling at 60 kilometres per hour. So if we're travelling at 65 here, we'd get double the risk of death or injury. Okay, and at 80, 32 times the risk of death or injury compared to travelling at our 60 k's per hour. So that's pretty sobering sort of thought there. So, and go on, another way to look at that is, and this figure here shows how the distance required for a car to stop increases for cars travelling 50, 60, 70, 80 and 90 k's. So up here we're doing 50 k's, 29 metres, and I think what they're saying is they're probably impacting someone at 30 metres here. I'm not quite sure what the impact, no impact means. But here we see we haven't even doubled the speed and we've more than doubled the stopping distance. Okay, so we can see that non-linear sort of element creeping in here again. Okay, so we've got some worked examples here. We're just going to calculate the kinetic energy of this Ford Focus. Its mass here, it says here, 1,300 kilograms, and it's traveling at 5 meters per second and then at 16 meters per second at speed. Okay, so firstly for the Ford Focus at 5 meters per second, its kinetic energy is, there's our formula there, a half mv squared, and that's equal to a half times 1,300 times 5 squared, and that gives us an answer there of 16.25 kilojoules. A kilo meaning 1,000, so it's 16.25 thousand joules. If we do the same calculation for the Ford Focus, but at 16 meters per second, we end up with this answer down here, 166.4 kilojoules. So we see it's a factor of about 10 difference. So that's pretty amazing difference. We've tripled the speed, but the energy in the impact is 10 times greater. So it's 10 times the energy of impact, even when we've only just tripled the speed. Okay, so we'll go on, and just a quick note on the energy's units of measure, how we measure it in. We've talked about this before. The joule is the energy, the unit for measuring quantities of energy. We also use the kilojoule because it's in this kj symbol here, and that's units of 1,000. We put that 10 to the 3. This here meaning 10 times 10 times 10, the 3 tens. Okay, so we also use megajoule, gigajoule, and terajoule. So mega is 1,000,000 joules, 10 to the 6. Gigajoule is 1 billion joules, and a terajoule is 1 trillion joules. Okay, so you could say a megajoule is 1,000 kilojoules, and a gigajoule is 1,000,000 kilojoules. You could have a chart that way as well. We need to keep that in mind. Okay, we've got another worked example here. Calculate the kinetic energy of a Ford territory. Now, the point being that a territory is a lot heavier. It's about 800 kilograms heavier. About 725 kilograms heavier. And once again, we're going to measure it at these two speeds. Okay, we're going to, work out the kinetic energy. So for the Ford territory, put it into the formula and we get 25.3 kilojoules. And compare that to the Focus. The Ford Focus was about 16 kilojoules. And then for the Ford territory at 16 meters per second, we got 259.2 kilojoules. And remember, I think that was about 166 kilojoules for the Ford Focus. So once again, and you can see there's this factor here of about 10 times. So once again, we can see the difference. There's the difference in the mass. Okay, gives you a little bit of increase in the energy of impact, but when we increase the speed, it has a much greater impact because of this v squared term here. Okay, now I've just got your turn to do some calculations here, and we're going to calculate for these three questions here. An 80 kilogram jogger running at 4 meters per second. We want to see his kinetic energy. A 10,000 kilogram bus traveling at 54 k's per hour, and 100 gram tennis ball hit at 30 meters per second, which is pretty fast. Remember, Usain Bolt runs at about 10 meters per second, and when he sprints, a bit less than that. So this is 3 times as fast. So stop the YouTube clip and have a go at those using the formula kinetic energy equals a half mv squared, and we'll see what answers you got. Okay, so for the first one, kinetic energy is 1/2 times, now the mass is 80 kilograms and the speed is 4, but we've got to square that. It's 4 times 4, so it's 1/2 times 80 times 4 times 4, and that comes to, by my calculations, 640 joules of energy. That's energy of motion, and that's meant to be a J. For the case of the bus, the kinetic energy is once again 1/2 times 10,000. That's 1,000. That's 10,000. Now, we got that in 54 kilometers per hour. To change that into meters per second, we just divide by 3.6, and it actually comes to 15. So it's 15 squared. And that comes to 1.125 megajoules. So heavy bus traveling fast, a lot of kinetic energy there. And the last one, this is 1/2. Now, it's only 100 grams, which is actually 0.1 of a kilogram times 30 all squared. And that comes to, by my calculations, 45 joules. Okay, so that just gives you a little bit how this is. So this is a person jogging. You're doing about 640 joules running at that speed. That's your energy of motion. A 10,000 kilogram bus traveling at that speed, a lot more. It's got a higher mass and a higher velocity, and very high velocity here, 30 meters per second, but only a very small mass. We ended up with a very small kinetic energy. Oh, pardon me. All right, so we'll just end that one there. We'll come back to a bit more of a discussion about energy in the next clip.